So hello guys, welcome back to the channel, and in today's video we'll be solving this inequality, that which one is a greater number, e raised to power pi or pi raised to power e. So basically the general solution for solving such kind of inequalities is using the calculus method. But I will be solving this problem with the help of two methods. The first one is obviously using the calculus, but the second method is actually very unique. I'll be using the thermodynamics second law to solve this inequality. So yeah, let's get started. So let's start off with the very first method. Now this method is a very traditional old school method because most of the teachers will use this only. And in fact, this method you will find in a lot of textbooks as well. So basically this is a very calculus driven approach. We'll use calculus to find the to prove this inequality. So yeah, let's start off. So what we have to prove is whether pi raised to power e or e raised to power pi, which one is a bigger number. So what I will be doing is I'm taking 1 by e pi power on both the sides. Now why so? Because you can see these alternative terms are getting cancelled. From here e and e gets cancelled, and from here pi and pi gets cancelled. So we are left with only symmetric terms such as pi raised to power 1 by pi and e raised to power 1 by e. Now from here I can reduce something of the type a raised to power 1 by a. So I've assumed a function fx, which is x raised to power 1 by x, or I can even write it as e raised to power ln x by x. Now we need to draw the graph of this function fx, and for that we will need the help of some critical points and the limit of the function at the boundary points. So yeah, so for critical points we need to first calculate the derivative or the f dash of the function. So f dash comes out to be x raised to power 1 by x into 1 minus ln x. And from here you can see this x raised to power 1 by x will never be 0 because 0 is not in its domain. But this 1 minus ln x can be 0 for x equal to e. And when we'll put x equal to e, this ln e becomes 1 and 1 minus 1 is 0. So now we have calculated that x equal to e is the critical point, but which one? It can be a local maxima or it can be a local minima. So for that we will need the help of the sine curve or the wavy curve method. So suppose this is a number line and this is e, and to the right hand side of e, which is basically the x greater than e region, and to the left hand side of e, it is the x less than e region. Now f dash x is uh, x raised to power 1 by x into 1 minus ln x. Now this portion will always be positive. What we have to check is basically this one, 1 minus ln x. Now this 1 minus ln x can be written as ln of e by x. Using the properties of log, we have written this as ln e by x. Now for x greater than e, this entire fraction will be less than 1. You can see e and x and something which is greater than e is basically 2.71, and something which is 2.7 greater than 2.71. So this entire fraction will be lesser than 1, and something ln of something which is lesser than 1 is negative. So in this region the graph will be decreasing and something like this. But on the other side, which is the x less than e side, if you look at this fraction, e by x fraction, this will be something which is greater than 1, and ln of something which is greater than 1 is positive. So in this region the graph will be increasing, just something like this. So from here you can see that x equal to e is the local maxima of the function, and in this case x equal to e will also be the global maxima of the function. You'll see it later when I'll draw the graph. You can see that x equal to e will also be the global maxima of the function. So yeah, now we have calculated the critical points, and now we need to just find the limit of the function at the boundary points. So the first boundary point is x equal to 0, and for limit x tending towards 0 plus. 0 plus is basically we are approaching 0 from the right hand side. So we can use the property of limit, and this comes out to be ln x by x where x tending towards 0 plus. Now you can see that whenever x is tending towards where x is tending towards 0, ln x is approaching towards negative infinity. Why so? Because if you look at the graph of ln x, it is something like this. This point is 1, and whenever you are approaching 0 from the right hand side, the value is approaching negative infinity. So for x tending towards 0 plus, ln x will be approaching negative infinity, and this x is also approaching 0. So the overall fraction will be approaching towards negative infinity. Now in this step I've just replaced the variable. I've taken x. Basically I'm approaching x towards negative infinity, and e raised to power x will result in a 0. So for x tending towards 0 plus, fx will be approaching to 0. Now for x tending towards infinity, this ln x by x, see this ln x is also approaching infinity, and x is also approaching infinity. So in this case we'll be using the L'Hopital rule, which says that the derivative of the numerator function upon the derivative of the denominator function. So now if we apply the limit, so for x approaching towards infinity, 1 by x will be approaching towards 0. So you can see this entire fraction will be approaching towards 0. So e raised to power 0, which is 1. So now we are good to go, and we can plot the rough graph of the function. So as you can see here, that this is x equal to e, and from 0 to e the graph is increasing, and for x tending towards 0 plus, the fx, the y is also approaching to 0, and from x equal to is e towards the positive infinity, the graph is decreasing and approaching its limiting value, which is 1. Basically y equal to 1 is the asymptote of the curve. Now you can see that pi 3, which is 3.14 approximately, and e, which is 2.71 approximately. So f of e will be greater than f of pi. So I've written that only here. E raised to power 1 by e is greater than pi raised to power 1 by pi. Now I've taken pi e power on both the sides again, just to get rid of the alternative terms. This e and e gets cancelled, and pi gets cancelled, and we are left with the classical inequality, that is e raised to power pi is greater than pi raised to power e. So yeah, you can see that we have proved this inequality using the first method. Now we'll be moving on towards the second method, which is basically the thermodynamical approach. So the second method is a very unique approach. Uh, you will not find this kind of solution in any books. I was going through a research paper, and there I found this approach. So I thought let's share it with you guys also. So I'll be solving this inequality with the help of the thermodynamics second law. This second method is completely based upon a thermodynamical approach. So let's get started. So you can see this is a reservoir which is at temperature T0, and we have a body of heat capacity C which is at temperature T1. Now here we are assuming that T1 is greater than T0. Now this will be very useful in the further calculations. Although you can assume anything like T0 greater than T1 or T1 greater than T0, it won't affect the calculation much. But like I'm assuming as T1 to be greater than T0. Now this reservoir and body both are brought in contact. So if two bodies of different temperatures are brought in contact, then both will acquire a same temperature after a long time. So you can see this reservoir will be maintained at the constant temperature T naught. So the body will have to come at temperature T naught to maintain the equilibrium. Now you can see that the heat released by the body. Now why the heat will be released? Because temperature T1 is higher than temperature T naught. So basically the body is going from a higher temperature to a lower temperature. So heat will be eventually released. So the heat released by body is given as C times change in temperature, that is C times T naught minus T1. Now the heat absorbed by reservoir will be negative of the heat released. That's simple. So basically that is C times T1 minus T naught. Now let me introduce you guys to the concept of entropy. So basically the qualitative definition of entropy is the measure of randomness. How random a body is, it defines its entropy basically. Suppose in gas the molecules move very fast. I mean they have a very high entropy because the randomness level in gas is much higher than that in liquids, and as compared to solids the randomness or the entropy of liquid is greater than that of solids. So the qualitatively we can say that entropy is a measure of randomness. Now, quantitatively, what the definition of entropy is: integration of change in heat, small change in heat in a reversible process upon temperature. This thing, the dq reversible upon temperature and integration of this. So from T1 to T 0 if we talk about the body, from T1 it's going from T1 to T 0 temperature, and dq is given as C times dt. So on integrating, we obtained the change in entropy of the body as C times ln T naught by T1. Now we are calling it as the first equation. Now similarly, if we talk about the change in entropy of the reservoir, we can use the same formula. But here in this case, since the reservoir is maintained at constant temperature, initial temperature is also T naught, this T naught, and the final temperature is also T naught. So in place of this t, we can write it as this t. We can write it as t naught, and we can remove this t naught from the integration sign, and we are left as integration of dq reversible, which is basically the change in heat of the reservoir, or the heat absorbed by reservoir, which is given by C times T1 minus T naught. So the change in entropy of the reservoir is basically C times T1 by T naught minus 1, and we are calling it as the second equation. Now for an irreversible process, the change in entropy of the system is greater than 0. Now this is the thermodynamics second law. Thermodynamics second law. So this is the thermodynamics second law. Just a second. Yes, this one. For an irreversible system, the change in entropy will be greater than 0. Now the system here comprises of the body and the reservoir. So the total change in entropy of the body plus the total change in entropy of the reservoir will be greater than 0. And what is the change in entropy of the body? That is C times ln T naught by T1. We have calculated this here. And the change in entropy of the reservoir is C times T1 by T naught minus 1. Now the C and C gets cancelled on both the sides. What we are left is T1 by T naught minus 1 plus ln times T naught by T1 greater than 0. Now the final step arrives is we can assume T1 as pi Kelvin and T naught as E Kelvin. Now earlier I've told you that T1 is greater than T naught. This T1 is greater than T naught. So this thing only I'm using here also. Although you can you can take any values of T1 in terms of pi, like you can take T1 as 100 pi, or T2 T naught as 100 E. It won't affect the calculation because at the end these constants will get cancelled out. So I'm taking T1 as to be pi Kelvin and T0 to be E Kelvin. Now pi by E minus 1 plus ln times E by pi should be greater than 0, substituting the values of pi and E in this expression. Now pi by E minus 1 should be greater than ln of pi by E, basically minus of ln E by pi, which in turn becomes the reciprocal. Now using the properties of the log, we can say that pi by E minus 1 is ln pi minus ln E, which is basically 1. Now this minus 1 and minus 1 gets cancelled out from here, and we are left with pi is greater than E times ln pi. Now pi is greater than ln of pi by pi raised to power E, and this is a very basic logarithmic inequality. On solving this, we are obtained this inequality, which we have proved with the help of the second law of thermodynamics. So yeah, that was it.